So now that we've got the idea that power series converge on a certain interval that has a certain radius and a certain center, we're going to look at some more of these power series, and finding the interval and radius of convergence is, that's what we're going to be doing for the homework, and we're just going to look at some examples of things that can happen. So our next one is this one, the sum from, that should say n equals 0, from n equals 0 to infinity of x to the n over n factorial. So they all, the nice thing is they're sort of a little bit standard. They all start the same way. They all start with a ratio test. So we're going to do a ratio test. We're going to look at what is a sub n over a sub n plus 1. We all know how to do that now. That's x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. We think about how things cancel. Looks like we're going to have x to the n on the top, and we're going to have n plus 1 on the bottom. So you can think about how that works if it's not clear. Then we look at what is the limit as n approaches infinity of the absolute value of a sub n over a sub n plus 1. And that is equal to the limit. That's not x to the n, it's just x. That's just x right there, not x to the n. I'm just going to rewrite that, x over n plus 1. Yeah, because there's one more x in the top than the bottom. So I have limit as n approaches infinity of the absolute value of x over n plus 1. Now, x is a fixed number. It's a real number. But n plus 1 is what's increasing. So no matter how big the x is, the n plus 1 will eventually get bigger, eventually get much bigger, and that limit is still 0 because the top is bounded, being a specified value, and the bottom is unbounded. All right, so this limit is 0 regardless of what the x is. So that's different from what we did last time, where we got an inequality and we had to solve the inequality. Well, here there's no inequality because there was no x. The x sort of went away in that limit, and we ended up with just 0. So this converges for all x. So the interval of convergence is negative infinity to infinity, and the radius of convergence is infinity. So this is an example of a series with an infinite radius of convergence. What, though, does that series converge to? We generally don't know that with these series unless, for a geometric series we had something sort of that we could see to begin with. This one we don't know, but it's a fun one to look at. So I'm going to look at this one it's also good to sort of look at what this means, these convergences. So we're saying that this x to the n over n factorial converges to something, but I don't know what. Well, let's look at some of the terms of it and see what it looks like. If I just do y equals 1, I get a horizontal line. If I go to 2 terms of the series, I get 1 plus x. It looks like a diagonal line. I add in a third term, so I have a second degree polynomial. Looks sort of archy. Oh, that wasn't good. Oh, that wasn't good at all. Where did we go? Oh, there we go. Jeez. Okay. So yeah, it looks sort of archy. And then third degree, giving you the third degree here. Here's fourth degree. What is it converging to, I wonder? What function is it starting to look like on this, especially if we look near 0? What function is it starting to look like? Yeah, let's put this one back on. Look, that's e to the x. So if we zoom out, see how nicely it corresponds until we get out a little bit farther. Now we can see how the e to the x goes to its horizontal asymptote, and the power series doesn't. But over here on the positive side, they're corresponding pretty well, right? So if we compare it to that e to the x, here's 2 terms: first degree, second degree, third degree, fourth degree, fifth degree, sixth degree. So it's starting to match better and better. It's going to take a lot of terms before, this starts to flatten out going this way. But if we had infinitely many terms, it would match up perfectly. So that one converges to e to the x. And we're actually going to see why it converges to e to the x later.